Okay, we're going to explore a little bit more on the equivalent resistance method of calculating currents and voltages in simple circuits. So this time we're going to use a bit more complicated circuit. We're going to use a combination of things that both have series elements and parallel elements. So the simplest of this would be a circuit that has both a parallel combination and a series element. Here, when I look at this circuit, I think of the combination of R1 and the equivalence of this parallel combination in my mind is a new equivalent resistance Req. So if R1, R2, and R3 are in this diagram, then R2 and R3 could be combined together into an equivalent resistance using our parallel combination method. Remember, when things are in parallel, whoops, not parallel, parallel, the equivalent resistance is a inverse relationship, and when they're in series, the equivalent resistance is a direct sum of the individual resistances. So based off of that, let's put in some numbers here. Let's go ahead and do a 10 volt battery, and we'll say that R1 is 10 ohms, R2 is 30 ohms, and R3 is 40 ohms. So I want to think of this picture, this resistance in my, or this circuit in my mind becomes a new resistor circuit, which is 10 ohms and R equivalent. So let's find out what R equivalent is. 1 over Req is going to equal 1 over 30 plus 1 over 40, which is equal to 0.0583 repeating. Therefore, my equivalent resistance is the inverse of this, which is equal to 17.1 ohms. So this one is 17.1 ohms, and I have a new circuit. I now look at this circuit and I see a series combination of two resistors. Therefore, this circuit becomes, in my mind, a new circuit which looks like this with a new equivalent resistance. In this case, I'm going to apply the series combination rule, which is sum 10 ohms plus 17.1 ohms, or 27.1 ohms of equivalent resistance. I am now down to the simplest circuit. I can now calculate the current. I in the circuit is V over R, which is 10 volts applied across that 27.1 ohm resistor, or 0.369 amps. Now, what current is that? Well, if we go back, now we start working our way backwards. If I go back up to this previous diagram, this current is flowing, this is the current 0.369 amps. Therefore, that is the same current here of 0.369 amps, because everywhere in a series combination, the current is the same, which means I now know the current flowing through the 10 ohm resistor, and I know the current flowing through the equivalent 17.1 ohm resistor, which means I can now go back a step mathematically and say that the voltage drop across the 10 ohm resistor is equal to the current through the 10 ohm resistor, which we know is 0.369 amps, times the resistance of the 10 ohm resistor, 10 ohms, or 3.69 volts. So I've dropped 3.69 volts of my available 10 volts across this 10 ohm resistor. which means I should drop the remainder of that across the equivalent resistance of 17.1 volts. So the voltage drop across the equivalent parallel combination would equal 0.369 times 17.1, which is equal to 6.31 volts. And you'll notice that the sum of those two is the 10 volts. Now I can go back another step. So here I'm going to fall back to my previous diagram. And I now know from the top end to the bottom end of the parallel combination that 6.31 volts is dropping across that combination. And we know that in a parallel situation, the same voltage drops across each piece of the parallel combination, which means that I have 6.31 volts dropping across my 30 ohm resistor and across my 40 ohm resistor. So now I can drop back mathematically and solve for the currents. So the current flowing through the 30 ohm resistor is going to equal the voltage drop, 6.31 volts dropping across 30 ohms, which gives me a current flowing there of 0.21 amps. The current flowing through the 40 ohm resistor would be the same 6.31 volts dropping across a 40 ohm resistor, which would equal 0.158 amps. You'll notice the sum of these two add up to the total current, because at a junction, the sum of the currents coming in and leaving the junction have to mathematically add up. So 0.361 or 0.369 amps splits when it gets to that junction, and some of it flows through the 30, some of it flows through the 40. The ratio of the amount that flows either way is governed by the ratio of those resistances. And you can see that by following this technique, you can get the voltage and current at any place in a simple circuit. To summarize, what we did is we started with our original diagram. We started with that, step one, what we call that. We recognized that that parallel combination could be represented by this second circuit, which was we began applying equivalent resistances, and we continue that process all the way down until we get to our simple circuit. Once we get our simple circuit, we apply Ohm's law to get our current in our simple circuit, and we can then step backwards each step at a time. We go back up one level until we have calculated V equals IR or I equals V over R for each element in our circuit. So the method of equivalent resistance works for many circuits and for sub-pieces of more complicated circuits. So one of the things we need to do is we need to be able to recognize when it applies and when it doesn't. And the trick is to identify whether or not it's just a combination of series and parallel combinations of resistances, in which case the technique works. If it has other voltage sources mixed in, then we have other techniques that would be used, the most likely being the method of Kirchhoff's laws or Norton equivalence. So let's take a quick look at a few diagrams. So if I had a diagram that looks something like this, I can make, whoops, that was really ugly, but I can make really complicated looking combinations of resistors and come back to where I started. And this is a method of parallel and series because I can identify each section as a combination that works. Here I come out of this and I'm going to split and I'm going to come back together and join back up. So I could make this into a combination like the following. These two resistors became this resistor. Now, these two resistors become a new series combination resistor. So this becomes a circuit like this. And then I see that that's a parallel combination. And so that becomes a circuit that looks like this. And then that one obviously is series and becomes our standard simple circuit. And we have something like that. So again, it can be more complicated and it can still be parallel and series. There are circuits that are not possible to build like this. Here, a classic version of this is something that looks like this. If we have two batteries involved, we can no longer combine these two, like let's take for example this resistor and this resistor. They look like they're in series from this battery, right? But there's an alternative path that can be followed. So these are truly not in series, and the same rule applies here. These look like they're in series, um, but then again, these two loops are in parallel with each other. So the method of equivalent resistance doesn't get used here. We would use a different technique. So recognizing when you can and can't use it is an important skill in utilizing the method of equivalent resistance.